speaker, Paul Lefebvre, will discuss the challenges and benefits from a scientific and project management perspective to help understand the role chiral chromatography plays in proving enantiomerically pure material. Go ahead, Doctor. Sorry, Paul. I think you're on mute.
Thank you. Sorry about that.
No problem.
So yes, thank you all, Nitin, Neelam, and everybody else for being here today and having me here today. So I want to talk to you about Enantiomerically and the work we do here related to chiral separations. Whoops. And so Enantiomerically itself is a contract CRO located in Milford, Massachusetts. We handle many projects, one of which we're here to talk about, which is the chiral molecules with single, multiple stereocenters, atrope isomers, diastereomers, all different types of compounds, with the goal of providing a scalable supply of material through chromatography to our customers, as well as use the chromatography to isolate impurities, both chiral and achiral, in nature. So with that, why we focus towards SFC as a means for our prep chromatography, and we do that. There are some chromatography benefits, and I think some of the other speakers will go into a little bit more. But the real from the purification standpoint, it's really comes down to the efficiency and the safety of your compound, I guess maybe is the best word, where the dry down is faster. There's not lots of water present. So really that CO2 that evaporates on fraction allows you to analyze the sample immediately, get the dry material and isolated material as fast as possible. So we tend to push all our projects towards SFC if that's doable. And we go from there, and I'll go through several different examples with you on that as we continue. Oops. So one of the keys to success, is not only just having the method, but being able to work efficiently. And that's one of the keys to purification is it's not just resolution. It's keeping the system up and running. It's getting material as fast as possible. Our customers don't necessarily care how we get there. They just care that we got there and they have pure material that they can do what they need to do with. But from a lab standpoint, all of these factors are super important. How can we increase the load? Are we looking at the right samples? Do we have to re-purify material? Can we run unattended, or do we have to be here? All these different factors go into every project that we do. And so just kind of run through some of these things. We've made numerous system improvements over the years to improve the productivity of and reliability and performance of the SFC systems. Most of these modifications have been incorporated into the newer SFC systems available, which we've worked with the manufacturers to provide the information and feedback to give these modifications. Some of these includes how the injections are done, which mixed versus modifier stream injection has an impact on the chromatographic peak shape, and if done right, if done poorly, you can really impact your productivity. Fraction collection timing, making sure your recovery is optimized based on your data signal and intensity. The ABPR is a big factor in SFC, providing that the back pressure on the outlet of the UV column can be varied if necessary, but it's also a potential Achilles heel of an SFC system, and can just die in the middle of the run, and then it screws up everything, and you're starting over again, and that's never fun for anybody. So we've worked through a much more rugged and reliable ABPR. as well as evaluating the pump performance and fraction collection design to overall improve the productivity of the system and uptime. But alternatively, kind of want to talk about some of the other things that go into potential efficiency gains that we have and we employ here to get successful results. You can look at a potential an intermediate, and you don't always have to resolve the final material. Looking at different feedstocks and the state of those feedstocks. Does it have to be fully pure? How about protecting your material or deprotecting, derivatizing it in some way, as Nitin just talked about, improved benefits there for diastereomeric crystallization, but it's also for chromatography, as well as partial enrichment, and reprocessing by multiple methods, or, and having a standard is super helpful. And looking at, the elution order of your racemates is really valuable, and the productivity of those. So just to run through some of these examples, looking at this valsartan purification, it has a chiral method that's been published on AD, very low productivity. But if you look at the penultimate material, it has, what is that, 10x or more than 10x, 30x the productivity to be purified. And then you take the chirally pure material to its final product, and just with a simple changing of the material, you get to the same place where you want it to be. Another example is with impurities here, and see this, we did a large batch of this project. It was great chiral separation, but with that chiral separation, we also there are 28% impurities present, and the option we had was to get it achirally clean and then do the chiral separations. We found that through stacked injections, we were able to stack the impurities out and generate high pure enantiomer 1 was the desired enantiomer, and fairly pure enantiomer 2 for this customer without and eliminated the need for the achiral cleanup. One of the nicer things is and similar to the previous material is the Bach protected material. Here's an example where the unprotected material, best method that we have, shows tailing, inadequate resolution, and as a result leads to poor prep loading. So very inefficient method. However, when we looked at the FMOC or the Bach material, we see that the Bach material, both give us much better peak shape, improved resolution. And when you take the Bach material up to prep chromatography, you get wonderful loading, great resolution, and everything is good. So then the other thing to think about as far as the feedstock and the enantiomers that you're interested in, E1 production of E1 is always more efficient than E2. So some you can look at if you have a standard, you can figure out which one is your desired material. The Perkle type columns that I think another speaker will be talking about actually are useful in that they can reverse the elution order of E1 and E2, so you can use that to your advantage, as well as the idea of a partially enriched feedstock, whether that's through synthetic means or diastereomeric crystallization, can also be a much more useful step where you know, and this is really comes in partnership with the chemist or the process chemist that's trying to achieve success. You know, they may have only gotten partially way there. Chromatography is easier to do from the as sort of a polish step going forward. So to demonstrate that, we did this sort of example, and we used warfarin as a test probe compound, and we made varying ratios of E1 and E2 for this. And you know, if you look at the racemic processing of this material, it's about you know, it's about 0.85 kkd. But what really gets interesting is if you look at the highly enriched material of E1, it's at 1.8 kkd for generating of E1 compared to, which is about 4+ times better than just starting from racemate, as well as, you know, even 7525 is 2x the speed at which it allows you to generate pure material. But if you look at the highly enriched E2 material, that's only about 2.5 times better than processing crude material, and really the result of that has to do with the peak shape on loading, and you get that fronting that occurs, and that fronting is interfering with the elution, or co-elute, begins to co-elute with the earlier eluting E1 material. So so taking this logic and you know, applying it towards a project that we did in house, we had a 85 gram separation that at lower loading we could get done in approximately 20 hours. Or if we do a much you know, so it's just a one-step, lower loading, lower productivity, get you done 20 hours. However, if you do this higher loading with the polishing step, we were able to process the 85 grams in the first pass in 6 hours, well, actually 4 hours. And then the valley fraction, which is the sort of the unresolved material, was pushed back through at this high load level to generate 80% E on the first pass. So a total of 6 hours to do this. And then that 40 grams of 80% E1 was then reprocessed. And that reprocessing only took, it took 4 hours. I think it actually only took 2 hours. That was a minor typo there. Took 2 hours to get done. And so overall, 8 to 10 hours to complete this. So yes. Oh no, it did take 4 hours. Yeah, that makes sense. Yes. 4 hours to complete that 40 grams. So total of 10 hours. So twice as fast, same chromatography, same method, just varying the loading and the fraction collection and the reprocessing to get it done twice as fast. The other approach we take is you mentioned this is multiple chiral centers. So the, maybe I would say typical, maybe not so typical, the approach that a lot of people like to use is one method gets you done. We actually don't like that. We found that it leads to long stack times, potential impurities that are co-eluting and differentiating between an impurity and an isomer, partially resolved peaks. So there's a lot of repolishing of each one of these peaks, so the recovery is lower. You know, in this instance, we see 7 isomers, not 8 as would expected from this 3 chiral center. And then, you know, then the question becomes is where's the 8th isomer and how do you find that 8th isomer? So the approach that we take is to actually screen and look for sort of a discrete set of peaks. And so in this example, we screened it by SFC. You see that there are methods that show multiple peaks, multiple peak shapes. multiple peak clusters. So based on the band shape retention, and we select a method to move to prep from there. So in this instance, we scaled to prep. We got 4 discrete fractions. The interesting part that we apply here is the use of UPLC data, and the UPLC data has the ability to resolve the enantiomer pairs, as you see in this top chromatogram here on the right. And what you see is there's 2 peaks. There's 4 peaks observed, which are the 4 sets of enantiomers present. So we use this UPLC method that resolves the enantiomer pairs to interrogate the fractions that we collected. And what we're able to see is that there's a single peak observed in fraction 1. Its corresponding peak is observed in fraction 2. There's a single peak observed in fraction 4. Its corresponding peak is observed in fraction 2. And there's 2 other peaks in fraction 2, as well as two discrete peaks in fraction 3. So with this data and this simplified prep SFC method, we're able to determine quickly that we've isolated 2 impurities, two isomers cleanly, and that there's 4 remaining isomers in fraction 2 and 2 remaining isomers in fraction 3. So we've just simplified the project down. We then take and screen that fraction 2, fraction 3. We find methods that should give us 4 peaks, 2 peaks. We take those on and isolate and take those to prep. We know where all our peaks are. We're able, no additional methods development to find that peak, no additional screenings required. And so we build this sort of tree with this that allows us to have the uniqueness through its HPLC retention time and different SFC retention times that allow us to verify that each one of these are unique isomers. And this allows us to process multiple chiral center samples in just a matter of a few hours for gram scale quantities of materials. Like I said, this example was in 3 stereo centers. We've gone up to as many as 5 stereo centers. That's been fun and challenging. And I don't recommend that, but it works. But it's just a lot more, a bigger tree that you get. And it's doable. So with that, just to summarize, good methods are required for good purification. And so even though you only see 1 peak, it doesn't mean that it's pure. So good methods are required, and optimization is useful, but it should be appropriate to the scale that you use. And over optimizing your method isn't necessary when the amount of material is small. Consider the source of the material and what you're trying to do to improve your efficiency. Just don't live in the black box. I have a racemate to resolve. There are other forms of that compound that exist, and that could be used for that chiral separation to get you where you're going to go. And good communication between the chemistry and chromatography can absolutely help you reduce the overall efforts required on both sides. And don't write out the chromatography unless you absolutely have to. So with that, I am done, and I will pass the baton to the next person.